Hey guys, today we're doing Leetcode 314 binary tree vertical order traversal. Essentially, this problem is just asking us to iterate over nodes in a binary tree, grouping those nodes by column, ordered from top to bottom, or root to leaf, and then left to right. So to make this a little bit more clear, let's hop into some examples. In the first example Leetcode provides us, we can see that we have 4 columns and 3 rows. The result we'd like to return is 9, 3, 15, 20, and 7. You can see that we can achieve this result by going row by row from left to right. Similarly, in the second example, we have 5 columns and 3 rows, and the result we'd like to return is 4, 9, 3, 0, 1, 8, and 7, which we can do by going from top to bottom and left to right. Note that for column 0, we first put in 3, and then in the third row where we have 2 numbers, we go from left to right, so 0 and then 1, rather than 3, 1, 0. Given that we'd like to iterate level by level from left to right, breadth first search is a great algorithm for this problem. We could essentially implement this by having a queue, and then having a default dictionary that maps from a column to a list of node IDs. Then we could go through a while loop while the queue isn't empty, add the current element to the dictionary, add its left and right child nodes to the queue. And once we break out of the while loop, we could iterate over the column indices in order and then put them into a list that we want to return, which is the format desired in this problem. The first step in solving this problem is just to check if we have a null root. Because if that's the case, we can just return an empty list. Now we can start off with the first step of initializing our queue. We will use a deck in Python, and then we'll pass in the root and the column index, which will start off at 0. So next we need to create our default dictionary. Which is a default dictionary of lists. And then we want to track the minimum and maximum column index seen so far. We don't have to do this. We could just sort the keys in the dictionary at the end, but that would be, n log n in the number of columns, and we can just keep track of that in constant space by using 2 variables like so. So we'll initialize our while loop, while queue, which tells us that we'll break out once the queue is empty. And then we will pop off the queue on the left side, which will give us our current node and column index. Then we can update our min and max variables with the minimum and maximum column indices we've seen so far. And then finally, we need to add our current element to the queue. So our key is the given column index, and then we'll append the current node's value to the list for that column index. Next, we'll check if the current node has a left child. If it does, we will append it. And we'll do the same thing for the right. Note here that when we go left, we subtract 1 from the column index. When we go right, we add 1 to the column index. Finally, we just need to put this dictionary into a list format that this problem expects. So we can implement a list as a result variable, and then we iterate for I in range mn to mx plus 1, and then we just append to that result list. So let's see if this answer works. Looks good on the first case. Let's try the remainders. Okay, submit it, and there we go. So this particular solution seems to be 41.8% for time complexity and 34.76 for space complexity. Let's talk about time and space complexity. You can see in the comments that I've outlined the time complexity for each line. So initializing a deck should be O of 1, same thing for a default dictionary, same thing for min and max variables. Now in our while loop, we're going to iterate over all the nodes in the tree, so it'll be O of the number of nodes. Each particular action we complete within this while loop should be constant time. So the whole while loop should take O of the number of nodes. Now for the fifth step, iterating over the column indices, this will take O of n time as well, because we are, in the worst case, having one node per column, and so we would be, in that case, taking O of the number of nodes in time. Now if we look at space complexity, we are storing, in the worst case, every single node in the deck at once. And same thing in our dictionary. So in the worst case here, we would be taking O of n space. So this algorithm runs in, assuming n is the number of nodes in the tree, O of n time, and O of n space. So a couple unique points for this question. You'll come across a lot of tree questions in interviews. Most of the time, it's easiest to solve them using depth first search and recursion, but this problem highlights a case where it's actually easier to solve using breadth first search iteratively. Another unique point here is if you're solving this question in Python, it really highlights the importance of the collections module. So typically whenever I use a queue in Python, I'm actually using a deck from the collections module, which lets you append and pop from both the left and the right. But when you're using it as a queue, you only pop from the left and append on the right. And also this default dictionary, which essentially just lets you not have to check if a key already exists in your dictionary, which can just save some boilerplate code. Collections also has some useful things like counter, which can give you a frequency counter for an iterable in Python. I'd encourage you to check it out. I'll put a link to it in the video description. Did you like this question? Do you have other questions you'd like me to solve? Let me know in the comments below. And be sure to like and subscribe if you enjoyed the video. Thanks, and have a great day.